Something is wrong with empty space, and the people who understand exactly how wrong it is have known about it for over half a century. They just never figured out how to tell you. Here is what you were taught. You were taught that the universe is mostly empty, that atoms are mostly empty, that the vast distances between stars and galaxies are filled with nothing, and that this emptiness is just the way things are, the default state, the background, the blank canvas that everything else sits on. That is wrong, not slightly wrong. Not wrong in the way that Newtonian gravity is wrong, where the errors only show up at extreme speeds or near black holes. This is wrong by a factor so large that the English language does not have a natural way to express it. The emptiness of the universe, the very thing you think you understand better than almost anything else in physics, represents the single largest disagreement between what our best theories predict and what we actually observe. The discrepancy is 10 to the power of 120. That is, a 1 followed by 120 zeros. For comparison, the total number of atoms in the observable universe is roughly 10 to the 80. The gap between what physics says empty space should contain and what it actually contains is 40 orders of magnitude larger than the number of atoms that exist. This is called the vacuum catastrophe. And if you have never heard of it, that should bother you, because it is not new, it is not speculative, it is not fringe. It has been sitting in the published literature since 1967, when a Soviet physicist named Yakov Zeldovich, a man who helped build nuclear weapons and taught himself theoretical physics without ever completing a formal university degree, wrote the paper that formalized the problem. That was 59 years ago. And in all that time, nobody has solved it. Nobody has come close to solving it. The greatest minds in theoretical physics have spent careers on it and produced nothing that the rest of the field considers convincing. That is the starting point, not the conclusion, the starting point, because the vacuum catastrophe is not just a bookkeeping error in the equations. It is telling you something about the nature of empty space that most physicists would rather not say out loud. The emptiness you think is nothing, the emptiness inside every atom in your body, the emptiness between you and the nearest star, the emptiness that fills the enormous voids between galaxy clusters, that emptiness should be the most energetic substance in the universe. It should be so violent with energy that matter itself would be impossible. Stars would be impossible. Chemistry would be impossible. You would be impossible. The fact that you exist, the fact that anything exists, requires the emptiness to be almost perfectly calm, and it is. It is calm to a degree of precision that no known mechanism in physics can explain. And here is the part that should keep you up tonight. That perfect, inexplicable calm might not last, because in 2012, when physicists at CERN measured the mass of the Higgs boson, a number came back that placed our vacuum, our emptiness, our ground state of reality, not in the stable region of the energy landscape, but in the metastable region, a ledge, a local minimum that is not the true minimum, which means the floor you are standing on, the emptiness that makes your existence possible, might not be the real floor. There might be a deeper level of empty beneath it. And if the universe ever finds it, if a single point in space ever tunnels down to that true vacuum, the transition would expand outward at the speed of light, rewriting the laws of physics as it goes. You would not see it coming. Light from the event and the event itself would arrive at the same moment. And everything, every atom, every star, every memory, every trace that any of this ever happened would be replaced by a kind of emptiness that does not include us. But we are getting ahead of ourselves. Before you can understand why the emptiness might end, you need to understand why it should not exist in the first place. And for that, you need to go back to 1909 to a laboratory in Manchester, England, where a New Zealander named Ernest Rutherford asked two of his students to do something that should have been boring. Hans Geiger and Ernest Marsden were firing alpha particles at a thin sheet of gold foil. Alpha particles are helium nuclei, tiny, fast, positively charged. The expectation under the prevailing model of the atom, the Thomson plum pudding model, was that all of them would pass straight through. The positive charge was supposed to be spread evenly across the atom, like raisins in a pudding, too diffuse to deflect anything. And most of the alpha particles did pass straight through. Roughly 7,990, 9 out of every 8,000 went right through the foil as if it were not there. But a few bounced back, not sideways, back. Some of them reversed direction entirely, deflecting at angles greater than 90 degrees. When Rutherford saw the data, he said it was almost as incredible as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. That quote has survived over a century because it captures something that the math alone does not. The genuine shock, the impossibility. What those bounce-back particles revealed was that the atom is not a diffuse pudding. Nearly all of its mass is concentrated in an absurdly small central nucleus. How small? The diameter of a hydrogen atom is roughly 106 picometers. The diameter of a proton, its nucleus, is about 0.84 femtometers. The ratio of volumes is approximately 2.5 times 10 to the 14th, which means an atom is roughly 99,999,999,999% empty space. Not mostly empty, not largely empty, almost entirely, mathematically, overwhelmingly, nothing. Think about what that means for you, sitting wherever you are right now. Your body contains roughly 7 billion atoms, and every single one of them is almost entirely void. If you could somehow remove all the empty space from every atom in every human being currently alive on Earth, all 8 billion of us, you could compress the remaining matter into a volume of about 1.6 cubic centimeters. A sugar cube. The entire human species, every person who has ever argued, loved, built cities, fought wars, written symphonies, and launched spacecraft, all of it would fit inside a sugar cube. Everything else is emptiness. Now here is the part that should unsettle you. That emptiness is not really empty. It cannot be. Quantum field theory, the most precisely tested framework in the history of science, accurate to 11 decimal places when predicting the magnetic moment of the electron, demands that even a perfect vacuum is seething with activity, virtual particle pairs blinking in and out of existence, quantum fields fluctuating at every point in space, energy that exists even when nothing else does. This is not speculation, it has measurable consequences. In 1947, Willis Lamb and Robert Rutherford measured a tiny shift in the energy levels of hydrogen that could only be explained by the interaction of the electron with these vacuum fluctuations. The Lamb shift. It matched the theoretical prediction. The vacuum was not empty. It was buzzing. A year later, Hendrik Casimir predicted something even more direct. If you place two uncharged metal plates close enough together in a vacuum, the restriction of which virtual particles can exist between the plates versus outside them, creates a measurable force pushing the plates together, the Casimir Effect. It was confirmed experimentally by Steve Lamoureux at the University of Washington in 1997, matching the prediction to within 5%. Empty space pushes things around. Empty space has energy. Empty space, according to the best physics we have, is not empty at all. So when you calculate how much energy should be in the vacuum, when you sum up all the contributions from all the quantum fields up to the Planck energy scale, the number you get is approximately 10 to the 112th joules per cubic meter. That is an almost incomprehensible density of energy, packed into every cubic meter of empty space, everywhere, always. And the number we actually observe, 5.36 times 10 to the negative 10 joules per cubic meter. The measured vacuum energy, the cosmological constant, the thing that is actually driving the expansion of the universe, is not just smaller than the prediction. It is 10 to the 120 times smaller, 120 orders of magnitude. That is not a rounding error. That is not a minor discrepancy. That is the worst disagreement between theory and observation in the entire history of physics. Nothing else comes close. Not by 10 orders of magnitude. Not by 50. By 120. Somehow, all that violent quantum energy, all those fluctuating fields, all that seething activity that we can measure with the Lamb shift and the Casimir effect, somehow almost all of it cancels out, almost perfectly, but not quite. A tiny, tiny residue remains, just enough to accelerate the expansion of the universe, and that residue is precisely the amount that allows galaxies to form, stars to ignite, planets to coalesce, and you to exist. If the leftover were even slightly larger, the universe would have blown apart before any structure could form. If it were exactly zero, the universe would be a very different place. It is not zero. It is a specific, absurdly small, positive number that nobody can derive from first principles, and nobody knows why. That is not a rhetorical flourish. That is the actual state of the field. As of today, February 2026, no accepted theory explains why the vacuum energy is what it is. 59 years after Zeldovich wrote the founding paper, after thousands of physicists and tens of thousands of papers, Antonio Padilla at the University of Nottingham, who has spent nearly 2 decades working on the problem, calls it one of the most awkward, embarrassing, difficult problems in theoretical physics. When a journalist once asked Gregory Gabadadze at New York University which theoretical proposal for solving it he favored, his answer was none of them. The emptiness of the universe is not the default. It is not the background. It is the single deepest mystery in physics. And the fact that you were never told this, the fact that you went through school and life thinking emptiness was the boring, obvious, well-understood part of reality, that is the first thing this story is going to fix. Because the emptiness gets worse from here, much worse. When you look outward, past your body, past the solar system, past the galaxy, the emptiness does not just continue. it organizes itself into structures that should not exist, holes in the universe so large that the standard model of cosmology cannot produce them. And you are inside one of them. To understand how wrong the emptiness is at the largest scales, you first need to feel how empty the universe is at scales you can almost visualize. And the best way to do that is with a basketball. Imagine the sun is a basketball, 24 centimeters across, sitting on a table in front of you. At that scale, the Earth is a 2-millimeter sphere, roughly the size of a mustard seed, sitting 26 meters away. That is almost the length of a basketball court. The Earth, everything you have ever known, every ocean and mountain and city and person, is a speck of grit sitting a basketball court away from a ball you could hold in one hand. Jupiter, the largest planet, the one so massive it warps the trajectories of comets and probably prevented the inner solar system from being sterilized by impacts during the early bombardment. Jupiter is a golf ball, and it is sitting 135 meters away from the basketball. Neptune, the outermost planet, is a ping pong ball sitting 770 meters down the road, nearly half a mile away. And between the basketball and the ping pong ball, there is, for all practical purposes, nothing. A few smaller balls, some gravel, mostly vacuum. Now here is where the model breaks your intuition. In this model, where the sun is a basketball, the nearest other star, Proxima Centauri, is a marble sitting approximately 4,200 miles away, roughly the distance from New York to Berlin. One basketball in New York, one marble in Berlin, and between them, nothing. That is the scale of emptiness between neighboring stars in our galaxy. The Voyager 1 spacecraft was launched on September 5th, 1977. It has been traveling through space for nearly 49 years. It is currently about 171 astronomical units from Earth, approximately 25.7 billion kilometers. That sounds like a lot, until you realize it crossed into interstellar space in August of 2012 and has been flying through the void between stars for over 13 years. And it will not approach another star system for roughly 40,000 years. 40,000 years are travel through emptiness, and Voyager is moving at about 17 kilometers per second, over 38,000 miles per hour. The Milky Way itself contains somewhere between 100 billion and 400 billion stars. That sounds crowded until you do the math. The average distance between stars in the disk of our galaxy is about 4 to 5 light years. The density works out to roughly 1 star per 284 cubic light years. If each star were a grain of sand 1 millimeter across, the nearest other grain would be roughly 30 kilometers away. You could fit the entire Milky Way's worth of sand grains, hundreds of billions of them, and the space between them would still be so vast that you could walk for days without seeing one. And then you leave the galaxy. Between galaxies, the emptiness deepens by another factor of roughly 1 million. In the interstellar medium, inside the Milky Way, there are about 1 million atoms per cubic meter. Still almost nothing, but something. In intergalactic space, between the galaxy clusters, the density drops to about 1 atom per cubic meter. 1 per cubic meter. Take the volume of the room you are sitting in and imagine 1 hydrogen atom floating somewhere in that space. That is the density of the universe between galaxies. All of this you probably knew already, at least in broad terms. Space is empty. The distances are incomprehensible. The matter is sparse. This is the standard picture you were given, and it is accurate as far as it goes. But here is where the picture breaks. In 1981, an astronomer named Robert Kirshner and two colleagues at the University of Michigan, Augustus Oemler and Paul Schechter, were conducting a survey of galaxy redshifts in the direction of the constellation Bootes. They were using the pencil beam technique, taking deep, narrow samples of the sky and cataloging the galaxies they found at various distances. It was methodical, unglamorous work, the kind of project that usually confirms what you already expected. The data came back wrong. In one of the survey volumes, a roughly spherical region centered about 700 million light-years from Earth, they found almost nothing. Not fewer galaxies than expected. Almost zero galaxies. Where the average density of the universe predicted roughly 2,000 galaxies in a region that size, the Bootes void contained about 60. A sphere 330 million light-years in diameter, roughly 2% of the observable universe's radius, and it was almost completely empty. Kirshner had stumbled onto the first confirmed cosmic void, and it was enormous. At the time of its discovery, it was the largest known structure in the universe, though structure feels like the wrong word for something defined by the absence of structure. Subsequent surveys in the 1980s and 90s revealed that the Bootes void was not a freak occurrence. The universe was full of voids, enormous, roughly spherical regions where the density of galaxies drops to a fraction of the cosmic average. The galaxy distribution, it turned out, was not random and uniform. It was organized into a vast web of filaments and walls, with galaxies clustered along the intersections and voids filling the spaces in between. The cosmic web, a foam-like structure where most of the volume is emptiness. To understand why this was disturbing, you need to understand what was supposed to happen. The standard model of cosmology, lambda CDM, predicts that the early universe's tiny density fluctuations, the faint ripples visible in the cosmic microwave background, should grow under gravity into exactly this kind of web structure. And it works. The simulations match the observations remarkably well. Voids are expected, but there is a limit to how big they should get and how empty they should be, given the age of the universe and the amplitude of the initial fluctuations. Some of the voids we have found push against those limits or blow past them. In 2004, a team led by Patricio Vielva at the Instituto de Física de Cantabria in Spain was analyzing data from the Wilkinson Microwave Anisotropy Probe, WMAP, the satellite that mapped the cosmic microwave background with unprecedented precision. They found a cold spot, a region about 5 degrees across, in the direction of the constellation Eridanus, where the CMB temperature was roughly 70 microkelvin colder than the cosmic mean. That does not sound like much until you realize that the entire range of temperature fluctuations in the CMB is only about 200 microkelvin. This spot was anomalously cold. At its deepest point, the deficit reached 150 microkelvin. The statistical probability of such a feature appearing by chance in the standard model was estimated by Cruz and colleagues in 2005 at less than 0.2%. Then, in 2015, Istvan Sapudi and colleagues at the University of Hawaii pointed a different instrument at the same region of sky They found a supervoid, a region approximately 1.8 billion light-years across, at a redshift of about 0.22, with a density roughly 14% below the cosmic average, the Eridanus supervoid. The idea was that photons passing through a large void lose energy due to the integrated Sachs-Wolf effect as the void stretches while they cross it, and this could explain the cold spot. But the numbers did not add up. The ISW imprint from a void of that size and depth in a standard model should account for only about 10 to 20% of the observed temperature deficit. Nadatha and colleagues confirmed this. The cold spot was too cold, or the void's effect was too strong. Studies of other supervoids found the same pattern. The observed ISW signals from large voids were 5.2 plus or minus 1.6 times stronger than lambda CDM predicted, a roughly 3 sigma tension, not yet a definitive contradiction, but deeply uncomfortable. And then there was the big one. In 1988, A.I. Kopylov at the Special Astrophysical Observatory of the Russian Academy of Sciences found a void 300 to 400 megaparsecs across, the giant void among the largest confirmed structures in the observable universe at the time. But even the giant void was not the most troubling discovery. The most troubling discovery was the one that included you. This is a good moment to talk about Fritz Zwicky, because Zwicky is the patron saint of noticing things about the universe that nobody wanted to hear. Fritz Zwicky was born in Bulgaria in 1898 to Swiss parents and ended up at the California Institute of Technology in 1925, where he would spend the rest of his career being brilliant, confrontational, and almost universally disliked by his colleagues. He was a compact, intense man with a volcanic temper and a habit of calling other astronomers spherical bastards, a designation he explained by saying that no matter which direction you looked at them from, they were still bastards. His daughter, Barbarina, later claimed he only used the phrase twice, and both times about Swiss politicians, not astronomers. Nobody who worked with Zwicky believed her. In 1933, Zwicky was studying the Coma cluster, a massive collection of over 1,000 galaxies, about 320 million light-years from Earth. He measured the velocities of the galaxies within the cluster and applied the virial theorem to estimate the cluster's total mass. The number he got was roughly 400 times larger than the mass you could account for by adding up all the visible matter, all the stars in all the galaxies. He called the missing component Dunkel Materie, dark matter. Nobody cared. Not for decades. Zwicky published the result, and the astronomical community essentially ignored it. Part of the reason was the messenger. Zwicky made enemies compulsively. He accused Walter Baade, his colleague at Mount Wilson, of being a Nazi. Baade, who was German-born and had remained in the United States during the war, was reportedly so terrified of Zwicky that he told colleagues he believed Zwicky was going to murder him. There was an incident involving a rattlesnake found in the dome of a telescope. Zwicky accused Baade of planting it. The truth was never established, but the deeper reason Zwicky was ignored is more uncomfortable. He was right. He was right about dark matter. He was right about neutron stars, which he predicted with Baade in 1934, 2 years before their theoretical basis was established, and 3 decades before the first one was observed. Kip Thorne later called their paper one of the most prescient documents in the history of physics. He was right about supernovae, which he named and classified. He was right about gravitational lensing, which he predicted in 1937, 42 years before it was first observed in 1979, and he was gradually, systematically pushed to the margins of his own field. He was kicked off the 200-inch telescope at Palomar, the most powerful instrument available, despite having personally discovered over 120 supernovae. He ranted about it to anyone who would listen, including a young graduate student named Robert Kirshner, who arrived at Caltech in the early 1970s. Kirshner later recalled the encounter. Zwicky, by then wearing an eye patch from an unrelated medical condition, told Kirshner the story of how he had once used a V-2 rocket in 1957 to launch what he called man-made moons, small metal pellets shot into space to prove artificial satellite launches were possible. Then Zwicky pivoted, as he always did, to his grievances. "Those spherical bastards threw me off the 200 goddamn inch telescope," he said. Kirshner, barely into his 20s, had no idea what to do with this information. Zwicky died in 1974. He never saw his dark matter prediction confirmed. He never saw gravitational lensing observed. He never saw the cosmic web mapped. He never saw the voids that Kirshner would discover 7 years after his death. He died believing, correctly, that the universe contains something vast and invisible that his colleagues refused to take seriously, and that the structures in the cosmos were stranger than anyone was willing to admit. The universe proved him right on every count. It just did it after he was gone. The reason Zwicky matters to this story is not just biographical, it is structural, because the pattern that defines Zwicky's career, noticing that the universe is deeply wrong and being ignored for it, is the same pattern that defines the vacuum catastrophe, the cold spot anomaly, and the void that you are about to learn you live inside. But that is not even the disturbing part. The disturbing part is what that void does to the one measurement that is supposed to tell us how fast the universe is expanding, and why two teams of Nobel-caliber physicists, using the best instruments ever built, have been getting answers that disagree by an amount that should be impossible. In 2013, a paper appeared on the ArcSiv preprint server that should have rewritten the front page of every science publication in the world. It did not. The authors were Ryan Keenan, Amy Barger, and Lennox Cowie, working with data from multiple galaxy surveys, including 2-mass redshift survey and the 6-degree field galaxy survey. What they found was a void, but not like the Bootsy's void, not 330 million light-years across. This one was approximately 2 billion light-years in diameter. Let that sit for a moment. 2 billion light-years. The observable universe is about 93 billion light-years across. This single void spans roughly 2% of the entire observable universe's diameter. It is the largest confirmed structure, or anti-structure, in the known cosmos. And here is the part that changes everything about how you think about your position in the universe. You are inside it. The Milky Way, the local group, the Virgo supercluster, and everything else within roughly 1 billion light-years of you sits inside the KBC void, named after its 3 discoverers. The local galaxy density within this void is roughly 15 to 20% below the cosmic mean. You are not observing this void from outside. You are embedded within it. You have been living inside an underdensity of the universe your entire life, and nobody told you because nobody had mapped it at sufficient scale until 2013. The existence of the KBC void is not seriously disputed. Multiple independent surveys have confirmed the underdensity. What is furiously disputed is what it means. Because in the standard model of cosmology, lambda CDM, a void this large should essentially not exist. In 2020, Moritz Halsbauer and colleagues at the University of Bonn calculated the probability within lambda CDM. The existence of the KBC void represents a 6.04 sigma tension with the model's predictions. 6 sigma. For context, the discovery threshold in particle physics is 5 sigma, which corresponds to a 1 in 3.5 million chance of being wrong. 6 sigma is roughly 1 in 500 million. The standard model of cosmology, the one that describes the large-scale structure of the universe, says that this void should not be here. But it is, and it gets worse, because the KBC void does not just sit there as a statistical embarrassment. It may be contaminating the most important measurement in all of cosmology. You have probably heard of the Hubble constant, even if you do not remember the details. It is the number that tells you how fast the universe is expanding. It connects a galaxy's distance from you to the speed at which it appears to be receding. A bigger Hubble constant means faster expansion. A smaller one means slower. The value matters because it sets the age, size, and fate of the entire universe. If you get the Hubble constant wrong, you get the universe wrong. There are 2 main ways to measure it. The first is to look at the cosmic microwave background, the afterglow of the Big Bang, and use the standard model of cosmology to predict what the expansion rate should be today, based on the conditions of the early universe. The Planck satellite did this with extraordinary precision and got a value of 67.36 plus or minus 0.54 kilometers per second per megaparsec. That is the early universe answer. The second way is to measure it directly. Find objects whose true brightness you know. Type Ia supernovae and Cepheid variable stars. Measure how dim they appear, calculate their distance, measure their redshift, and work out the expansion rate from the local universe. Adam Ries and the SH0ES collaboration, using both the Hubble Space Telescope and the James Webb Space Telescope, published their most recent measurement in 2205. Their value is 73.49 plus or minus 0.9, 3 kilometers per second per megaparsec. Those 2 numbers do not agree. The gap between them is approximately 6 kilometers per second per megaparsec. That might not sound like much until you understand the error bars. Both measurements claim very high precision. The statistical tension between them is now approximately 6 sigma, 1 in 3.5 million odds that this is a coincidence. This is the Hubble tension, and it has been growing steadily more severe for over a decade. Every time someone measures it more carefully, with better instruments, with more data, the 2 numbers refuse to converge. The James Webb Space Telescope was supposed to resolve the tension by ruling out systematic errors in the Cepheid distance ladder. It did not. In 2004, JWST data confirmed the Cepheid measurements at 8.2 sigma significance, effectively eliminating the most popular proposed explanation for the discrepancy. Now here is where the KBC void enters the story. If you are sitting inside a large underdensity, a region where the local matter density is significantly below the cosmic mean, then the local expansion rate would be biased high. Matter gravitationally slows the expansion. Less matter nearby means less deceleration, which means locally measured expansion looks faster than the cosmic average. In other words, if we live inside a void, the local measurement of the Hubble constant would naturally come out higher than the value predicted from the early universe. In 2200, Indranil Banik and Vasilios Kalaitsidis published a paper in the monthly notices of the Royal Astronomical Society showing exactly this. Using baryon acoustic oscillation data, including results from the dark energy spectroscopic instrument, they demonstrated that the KBC void hypothesis reduces the Hubble tension from 3.8 sigma to approximately 1.1 to 1.3 sigma. Statistically, this is the difference between a crisis and a non-problem. Their model was 10 to the 8th power times more likely than the standard void-free lambda CDM explanation. But there is a cost, because the void that solves the Hubble tension is the same void that should not exist in lambda CDM. You cannot use the void to fix the expansion measurement and then pretend the void is consistent with the model whose measurement it is fixing. Either the void is real and lambda CDM has a deeper problem than the Hubble tension, or the void is somehow consistent with lambda CDM and something else is causing the tension. There is no version of this where everything is fine. The choice is between a measurement crisis and a cosmological model crisis. Pick one. This is the nature of the emptiness at the largest scales. It is not just background. It is not passive. The emptiness is doing something. It is pushing measurements apart, creating tensions that the smartest people in physics cannot resolve, and sitting there as an impossible statistical anomaly in the very model that is supposed to describe the universe. And none of this would have been discovered if it were not for a chain of human beings who were, in various ways, punished for looking too carefully at what the universe was doing. Robert Kirshner, who found the first cosmic void in 1981, went on to build one of the most influential astronomy programs in the country at Harvard, where he chaired the astronomy department from 1990 to 1997. But his most lasting contribution was not the Bootes void. It was his students. Kirshner had a talent for mentoring people who would go on to upend cosmology. Two of them would share a Nobel Prize. One of them is at the center of the Hubble tension right now. Brian Schmidt arrived at Harvard for his PhD in 1989. He was Australian by way of Montana, gregarious and sharp, the kind of student who could work a telescope all night and still be making jokes at breakfast. He finished his doctorate in 1993 and went to the Australian National University, where he would co-found the High-Z Supernova Search Team in late 1994. Adam Rees arrived at Harvard shortly after Schmidt left, starting his PhD in 1990. Rees was different, quieter. Kirshner later recalled that Rees did not like staying up at night observing. He preferred to analyze data in his slippers, but his analytical ability was formidable, and Kirshner put him to work on a project that would change everything. Both Schmidt's team and a competing group led by Saul Perlmutter at Lawrence Berkeley National Laboratory were trying to measure the deceleration of the universe's expansion. The expectation, nearly universal in the mid-1990s, was that gravity should be slowing the expansion down. The question was how fast. The answer would determine whether the universe would expand forever, slow to a stop, or collapse back on itself? It was the biggest open question in cosmology. Ries was leading the data analysis for Schmidt's team. In late 1997, the numbers started coming in, and they were wrong. Not wrong in the sense of errors, wrong in the sense of impossible. The distant Type Ia supernovae were dimmer than they should have been, not brighter, which would mean the universe was decelerating faster than expected. Dimmer, which meant the supernovae were farther away than predicted, which meant the expansion was not decelerating at all. It was accelerating. Ries emailed the team on January 12, 1998, at 6:36 p.m. The message read, in part, "The results are very surprising, shocking even. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers, after all." 4 days earlier, Brian Schmidt had emailed Ries with a subject line that read simply, "Hello, Lambda." Lambda, the cosmological constant, the thing Einstein had introduced to keep the universe static, then abandoned, calling it his greatest blunder. It was back, and it was real. When Ries showed the data to Kirshner, his thesis advisor, the man who had discovered the first cosmic void 17 years earlier, Kirshner could not believe it. He made the team redo the entire analysis from scratch. When the result held, Kirshner said the horrible truth dawned on him. The universe was not just expanding, it was accelerating. Something was pushing it apart. Something with roughly 68% of the total energy of the universe. Something that filled all of empty space, and nobody had any idea what it was. Perlmutter's team reached the same conclusion independently. Both groups published in 1998 and 1999. Science magazine named it the breakthrough of the year. Michael Turner at the University of Chicago coined the term dark energy because nobody could think of anything better. In 2011, Perlmutter, Schmidt, and Ries shared the Nobel Prize in Physics. Kirshner, who had trained 2 of the 3 laureates and led the program that produced the result, was not among the recipients. The Nobel is limited to 3, but there is a deeper irony here that connects directly to the emptiness. Einstein introduced the cosmological constant, lambda, in 1917 to prevent the universe from expanding. He thought the universe was static, and lambda was his way of propping it up. When Hubble's observations showed the universe was expanding, Einstein dropped lambda, calling it unnecessary. Now it turned out the universe was not just expanding, but accelerating, and lambda was real. But not for the reason Einstein wanted. Einstein used lambda to oppose expansion. The actual lambda drives expansion. He was right about the existence of the term and wrong about its sign, its meaning, and its purpose. The universe had taken his correction and inverted it, and the woman who contributed more than almost anyone to proving that the universe's matter budget was wrong, who showed that galaxies were spinning in ways that demanded invisible mass, never received the Nobel at all. Vera Rubin was born on July 23, 1928, in Philadelphia. She knew she wanted to be an astronomer from the time she was a child, lying in her bed, watching the stars through her window and tracking their arcs across the sky. Her high school physics teacher told her to stay away from science. She applied to Princeton for graduate school and was rejected. The astronomy department did not admit women. This was not an informal policy. It was a formal one. Women were not admitted to Princeton's astronomy program until 1975. Rubin got her master's at Cornell and her doctorate at Georgetown. Her master's thesis, presented at the American Astronomical Society in 1950, proposed that galaxies might exhibit large-scale coherent motion beyond the Hubble flow. It was met with what she later described as a chilly reception. Her doctoral thesis was initially rejected for publication by the Astrophysical Journal on the recommendation of Subramanian Chandrasekhar, who at the time was the journal's editor. The irony is that Chandrasekhar himself had been subjected to similar dismissal by Eddington decades earlier. Patterns repeat. In 1965, Rubin became the first woman permitted to observe at Palomar Observatory, home of the 200-inch telescope that Zwicky had been kicked off of. When she arrived, she discovered there was no women's restroom. The observatory had existed since 1948. In 17 years, nobody had thought to install one. Rubin reportedly cut out a paper figure of a woman in a skirt and taped it to the door of the men's room. "There you go," she said. "Now you have a ladies' room." At the Carnegie Institution's Department of Terrestrial Magnetism, starting in 1965, Rubin teamed up with instrument builder Kent Ford, whose image tube spectrograph could measure galaxy rotation curves with unprecedented sensitivity. They began with the Andromeda Galaxy, M31. The work was painstaking. They would observe at Kitt Peak, waiting hours for the telescope to collect enough photons, eating ice cream cones to stay awake during the long exposures. 4 cones in, Rubin could draw Andromeda's rotation curve by eye. What the curve showed was impossible under standard gravitational physics. The stars at the outer edges of Andromeda were moving just as fast as the stars near the center. They should have been moving slower, much slower, because the visible mass of the galaxy was concentrated toward the middle. The curve was flat, and a flat rotation curve means there is mass out there that you cannot see. A lot of mass, roughly 10 times as much invisible mass as visible mass, extending far beyond the visible edge of the galaxy like an enormous, invisible halo. Rubin and Ford published their Andromeda results in 1970. Between 1976 and 1986, they surveyed dozens of additional spiral galaxies. Every single one showed the same flat rotation curve. Every single one demanded dark matter. This was the observational confirmation of what Zwicky had claimed 43 years earlier with the Coma cluster. The universe was full of invisible mass, and the astronomical community, which had ignored Zwicky for decades, had no choice but to accept it. Rubin won virtually every major prize in astronomy. The National Medal of Science in 1993, the Royal Astronomical Society's Gold Medal, the first woman to receive it since Caroline Herschel in 1828, election to the National Academy of Sciences, but never the Nobel. Emily Levesque, an astrophysicist at the University of Washington, called it a glaring omission on the Nobel Committee's part. Rubin died on December 25, 2016. The Nobel Prize cannot be awarded posthumously. Sarah Horst, a planetary scientist at Johns Hopkins, tweeted after Rubin's death that from now on, whenever anyone argues with her about Nobel Prizes, she would just say, "Vera Rubin," and walk away. All 4 of Rubin's children became scientists. Her legacy is literally genetic. But the professional recognition she deserved in her lifetime, the one prize that would have told every girl watching the stars from her bedroom window that the gatekeepers cannot hold the gate forever, that prize remained as invisible as the stuff she discovered. In 2019, the Large Synoptic Survey Telescope was renamed the Vera C. Rubin Observatory. When it begins full operations, it will discover hundreds of thousands of supernovae per year and map dark matter with a precision Rubin could not have imagined. Her name will be on the instrument. Her Nobel will remain unawarded. Here is the connection that ties Rubin to this story about emptiness. Rubin proved the universe is filled with invisible mass, roughly 5 times as much dark matter as ordinary matter. The universe should be heavier than it looks. And yet, even with all that invisible mass included, even with the dark matter halo surrounding every galaxy, the universe is still overwhelmingly, anomalously, inexplicably empty. Dark matter does not solve the emptiness problem. It makes it stranger. Because now the question is not just why the visible universe is so empty. The question is why the universe, including all its invisible mass, is still so much emptier than the vacuum energy should allow. And that brings us to a correction that matters. You have probably heard the statistic that 95% of the universe is missing. That is misleading. Dark matter and dark energy are not missing. We can measure their gravitational effects. We can map dark matter through gravitational lensing. We can quantify dark energy through the acceleration of the expansion. They are not absent from the ledger. They are on the ledger. What is missing is an explanation for what they are. And the vacuum catastrophe, the 120 orders of magnitude problem, is a completely separate and far deeper crisis. The vacuum catastrophe is not about what is missing from the universe. It is about what should be there and is not. The energy that quantum field theory demands should fill every cubic meter of space. The energy that would make the universe uninhabitable if it were actually present. That energy is the real missing quantity. And unlike dark matter, which we can at least detect indirectly, the missing vacuum energy leaves no trace at all. It is not there, and nobody knows where it went. Or whether went is even the right word, because maybe it was never there in the first place, and the equations that predict it are telling us something we have not yet learned how to hear. But here is what should genuinely disturb you about all of this. The voids, the Hubble tension, the dark matter halos, the missing vacuum energy, these are all symptoms. They are all manifestations of the same underlying disease. Something is wrong with empty space, and the disease does not live in the observational data. It does not live in the cosmic voids or the galaxy surveys or the CMB maps. It lives in the vacuum itself, in the gap between what the vacuum should contain and what it does contain. 120 orders of magnitude of wrongness. And the people who understand this problem best, who have spent their careers trying to close that gap, will tell you, if you catch them in an honest moment, that they have no idea what the answer is. And the gap is not getting smaller, it is getting more precise. The problem with the vacuum has a history, and the history is, in its own way, as disturbing as the problem itself, because the people who first noticed it were not working on cosmology. They were not gazing at the stars. They were doing quantum mechanics in the first decades of the 20th century, and they stumbled onto a number so absurd that they chose, reasonably enough at the time, to ignore it. Wolfgang Nernst, the German physical chemist who won the Nobel Prize in 1920 for his work on thermodynamics, was the first to take a serious look. In 1916, Nernst calculated the energy density of the zero-point radiation implied by the then-new quantum theory. His answer was, in his own words, quite enormous, roughly 150 grams per cubic centimeter, which might not sound like much until you realize he was describing the energy density of nothing, of empty space, of the vacuum. 150 grams per cubic centimeter is about 10 times the density of lead. Ernst found this peculiar, but did not consider it a crisis. Quantum theory was young. The implications were unclear. Then Wolfgang Pauli noticed the gravity. Pauli, one of the sharpest and most acerbic minds in the history of physics, the man who would formulate the exclusion principle and predict the neutrino, realized in the 1920s that if you took Nernst's zero-point energy seriously and asked what its gravitational effects would be, you got an answer that was obviously insane. The energy density of the vacuum would curve space-time so violently that the observable universe could not even reach the size of the moon. The radius of the universe, if the vacuum energy were what quantum mechanics said it was, would be smaller than the distance from the Earth to its own satellite. Pauli reportedly found this amusing rather than alarming. He did what any reasonable physicist in the 1920s would do. He assumed the calculation was telling him that the vacuum energy simply did not gravitate, that it was real in some quantum mechanical sense, but did not couple to gravity. Problem dismissed. Move on. For the next 4 decades, the physics community largely followed Pauli's lead. The vacuum energy was treated as a computational artifact, a quirk of the formalism, something you subtracted away during renormalization and did not think about. Nobody worried about it because nobody had a reason to worry about it. General relativity was well tested. Quantum field theory was spectacularly successful. As long as you did not ask what happened when the two met in the vacuum, everything was fine. Then Yakov Zeldovich ruined everything. Zeldovich is one of the most remarkable figures in 20th century physics, and the fact that he is not a household name tells you something about how the history of science gets written. He was born on March 8, 1914, in Minsk, in what was then the Russian Empire. He never completed a formal university education. He went to work at the Institute of Chemical Physics in Leningrad as a laboratory assistant at the age of 17 and taught himself theoretical physics by reading everything he could find. By 1936, at the age of 22, he had earned the Soviet equivalent of a PhD for his work on the theory of catalysis. By the early 1940s, he was one of the leading figures in the Soviet nuclear weapons program, working alongside Andrei Sakharov on thermonuclear bomb design. He received the Hero of Socialist Labor Award, 3 times the highest civilian honor in the Soviet Union, given only to those who had made exceptional contributions to the state. His contributions to weapons physics were so classified that his identity was kept secret from the international scientific community for years. In the 1960s, with the weapons work behind him, Zeldovich pivoted to astrophysics. The pivot was not a retirement project. It was a second career of staggering productivity, working independently from the West, mostly behind the Iron Curtain, unable to travel outside the Soviet bloc until 1982 due to his classified status. Zeldovich made contributions across an absurd range of topics. He and Edwin Salpeter independently proposed in 1964 that quasars were powered by accretion disks around supermassive objects. He and Rashid Sunyaev predicted the Sunyaev-Zeldovich effect, the distortion of the cosmic microwave background by hot gas in galaxy clusters. which became one of the key tools for mapping the large-scale structure of the universe. In 1973, Stephen Hawking visited Moscow. During the visit, Zeldovich and Alexei Starobinsky showed Hawking their calculation that rotating black holes should emit particles. The argument was incomplete, and Hawking knew it, but it planted a seed. Within months, Hawking had worked out the full theory. Black holes radiate. Hawking radiation, one of the most celebrated results in theoretical physics. It started with Zeldovich, but the contribution that matters most for this story came in 1967 and 1968, when Zeldovich published a paper in Soviet Physics Aspeki titled The Cosmological Constant and the Theory of Elementary Particles. It is the founding document of the modern vacuum catastrophe. What Zeldovich did was simple and devastating. He took the zero-point energy of quantum fields, the same energy that Nernst had calculated and Pauli had dismissed, and he connected it explicitly to general relativity. He showed that the vacuum energy of quantum field theory is mathematically identical to the cosmological constant in Einstein's field equations. They are the same thing. The energy of empty space and the term that governs the expansion or contraction of the universe are not two separate problems. They are one problem. And the one problem is that they disagree by 120 orders of magnitude. Zeldovich knew this was catastrophic. He tried to find a mechanism that would cancel the vacuum energy naturally, some symmetry or dynamical process that would drive it to zero. He failed. He proposed that perhaps the contributions from bosonic and fermionic fields might cancel each other, an idea that would later be refined into supersymmetry. But supersymmetry, even in its most optimistic formulations, does not solve the problem. It reduces the discrepancy from 120 orders of magnitude to roughly 60. 60 orders of magnitude is better than 120. It is still the worst prediction in science. Zeldovich died on December 2nd, 1982, at the age of 73. He died 11 years before the discovery of the accelerating expansion of the universe, the discovery made by Kirshner's students, the discovery that proved the cosmological constant was not zero, that it was real, that the vacuum energy, the thing he had spent the last 2 decades of his life agonizing over, was actually there. Small, inexplicable, but there. He never knew. He went to his grave thinking the cosmological constant problem was a theoretical puzzle. He did not live to see it become an observational crisis. Now here is where the problem becomes truly disturbing. Not just embarrassing, not just awkward, disturbing in a way that challenges what you think physics is supposed to do. The standard telling of the vacuum catastrophe focuses on the size of the discrepancy, 120 orders of magnitude. Worst prediction ever. That framing makes it sound like an error, like somebody plugged in the wrong number and the answer came out too big. But that is not what happened. The prediction is correct. Quantum field theory is the most precisely tested theory in the history of science. Its prediction for the anomalous magnetic moment of the electron matches experiment to better than 1 part in 10 billion. The theory works. The calculation is sound. The energy should be there. And the observation is also correct. The accelerating expansion of the universe has been confirmed by multiple independent methods, by type 1 supernovae, by the cosmic microwave background, by baryon acoustic oscillations. by gravitational lensing. The cosmological constant is approximately 5.36 times 10 to the negative 10 joules per cubic meter. This is not in dispute. So you have a theory that is correct and an observation that is correct, and they disagree by 120 orders of magnitude. This is not a rounding error. This is two correct answers to the same question that have nothing to do with each other, and nobody knows why. There is one proposal that works, mathematically speaking, and it is the one that most physicists find the most disturbing. In 1987, the same year Zeldovich died, Steven Weinberg published a paper in Physical Review Letters that changed the conversation. Weinberg, who had shared the 1979 Nobel Prize for his work on electroweak unification, approached the cosmological constant problem from a completely different angle. He did not try to calculate the vacuum energy from first principles. He did not try to find the cancellation mechanism. Instead, he asked a simple question. If the cosmological constant could take any value across a large number of possible universes, what values would be compatible with the existence of observers? The answer was remarkably specific. If the cosmological constant were more than roughly 1 or 2 orders of magnitude larger than the observed value, galaxies could not form. The vacuum energy would drive the expansion so fast that matter would never have time to clump together under gravity. No galaxies means no stars. No stars means no planets. No planets means no observers. Weinberg predicted in 1987 that the cosmological constant should be small but non-zero, roughly 5 to 10 times the present matter density. In 1998, 11 years later, Perlmutter, Schmidt, and Ries discovered the accelerating expansion and measured a cosmological constant that fell precisely within Weinberg's predicted range. This is either the most impressive prediction in the history of cosmology, or the most disturbing, depending on how you feel about the implications. Because Weinberg's argument does not explain why the cosmological constant is small. It does not identify a physical mechanism. It does not derive the value from any theory. What it does is change the question. Instead of asking, why is the vacuum energy this value? It asks, given that observers exist, what range of values is compatible with their existence? The answer is a narrow window. We observe a value in that window. Therefore, we exist. This is the anthropic argument, and it requires a landscape. If the cosmological constant is not set by any physical mechanism, if there is no equation that outputs the value 5.36 times 10 to the negative 10, then the value must vary. There must be other regions, other domains, other universes where it takes different values. Most of those values would be incompatible with life. We find ourselves in one of the rare pockets where the value allows structure to form. We do not observe the value because physics demands it. We observe it because we could not exist anywhere else. The string theory landscape provides exactly this kind of framework. In the early 2000s, researchers realized that string theory does not predict a single vacuum state. It predicts a vast number of them. Michael Douglas estimated the number at roughly 10 to the 500th power. More recent calculations have pushed this to 10 to the 270 2000th power distinct flux vacua. Each vacuum state has different physical constants, different particle masses, different cosmological constants. Leonard Susskind formalized this in a 2003 paper titled The Anthropic Landscape of String Theory. Of the 10 to the 500th power vacua, roughly 10 to the 380th have cosmological constants in the anthropologically viable range. Think about what that means. The emptiness of our vacuum is not explained by physics. It is explained by selection. Among an inconceivably large number of possible vacuum states, we happen to inhabit one of the tiny fraction where the vacuum energy is low enough for galaxies to form and high enough to not be zero. There is no deeper reason. There is no mechanism. There is no equation that spits out the answer. The emptiness just is what it is, and we are here because it is. This is the part that should make you angry. Not at the physics. The physics is honest. But at the fact that this has been the state of affairs for decades and you were never told. The vacuum catastrophe is not an obscure technical puzzle. It is the single largest numerical discrepancy in the history of quantitative science. It strikes at the heart of what physics is supposed to do, which is explain why the universe has the properties it has. And the best available response from the theoretical physics community is, essentially, that there is no explanation. The universe is this empty, because if it were not, we would not be here to notice. That is not an explanation. It is a surrender, a sophisticated, mathematically rigorous surrender, but a surrender nonetheless. And here is the part that makes the surrender even harder to accept. In his 1989 review in Reviews of Modern Physics, Weinberg distinguished two versions of the cosmological constant problem. The old problem was why the vacuum energy is so small. The new problem was the cosmic coincidence. Why is the vacuum energy density roughly the same order of magnitude as the matter density right now, in this particular epoch of cosmic history? Not a billion years ago, when matter dominated overwhelmingly. Not a billion years from now, when the vacuum energy will dominate overwhelmingly. Right now, in the narrow window where we happen to exist, the two problems together, the smallness and the coincidence, form a trap that no known physics can escape. Catherine Fries, a theoretical astrophysicist at the University of Texas at Austin, has described the observed cosmological constant as very weird, even weirder than zero. Zero would at least suggest a symmetry, some principle that forces the value to vanish exactly. But the observed value is not zero. It is a tiny, specific, positive number that seems to have no reason to be what it is. It is as if someone asked you to pick a number between 0 and 10 to the 100, and the answer turned out to be 0.000007. Not 0, not 1, not any number your mind would naturally land on. A number so close to 0 that it might as well be 0, but is not. And the difference between it and 0 determines whether the universe expands forever into emptiness or not. This is where we are. The emptiness of the universe is a catastrophe that physics has acknowledged and cannot fix. The voids are too large. The Hubble constant disagrees with itself. The vacuum energy is 120 orders of magnitude too small. And the only framework that predicts the observed value requires accepting that our universe is one bubble in a foam of 10 to the 500th power possible realities, selected not by physics, but by the brute fact that we are here. The emptiness is not a background. It is the central mystery of modern physics, and it has been sitting there, largely unaddressed, for almost 60 years. But even that is not the worst part, because so far we have been talking about the emptiness as a static problem, a fixed discrepancy, A number that is wrong, but at least stable. The vacuum energy is what it is. Too small, too weird, too coincidental. But at least it is not changing. Except it might be. And the universe is definitely getting emptier. Either second. On January 8th, 1998, Brian Schmidt sat down at his computer in Canberra and typed an email to Adam Rees. The subject line was 2 words, "Hello Lambda." The casualness of it belied what was happening underneath. Both men knew that the data they were looking at, the dimming of distant Type Ia supernovae, implied something that the entire cosmological community had assumed was impossible. The expansion of the universe was not slowing down. It was speeding up. Something was pushing the universe apart, and that something was winning. 4 days later, Rees sent his now famous reply to the full team. The results are very surprising, shocking even. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers, after all. That last line has always stayed with me. We are observers, after all. It is a plea for empiricism in the face of something that felt wrong. The data was telling them that roughly 68% of the total energy content of the universe was something nobody had predicted, nobody understood, and nobody could detect directly. It filled all of space. It had no apparent source, and it was driving the expansion to accelerate, pushing every galaxy away from every other galaxy faster and faster, with no known mechanism to stop it. Saul Perlmutter's team at Lawrence Berkeley, working independently with different supernovae and different analysis methods, reached the same conclusion at almost the same time. Both groups published. The result was confirmed and reconfirmed over the following years by the cosmic microwave background data from WMAP and later Planck, by baryon acoustic oscillation measurements, by gravitational lensing surveys. Dark energy was real, and it made the emptiness problem infinitely worse. Because dark energy does not just mean the universe is expanding faster, it means the universe is emptying itself, actively and permanently. And the process has consequences that even dedicated science enthusiasts have never fully confronted. Start with the cosmic event horizon. In a universe with a positive cosmological constant, there is a maximum distance beyond which light emitted today will never reach you. Not because it is too far away right now, but because the space between you and the source is expanding faster than the light can cross it. This horizon currently sits at roughly 16 billion light-years in proper distance. Beyond that boundary, the universe is, for all practical purposes, gone. You will never receive a signal from anything beyond the cosmic event horizon. It will never influence you. You will never observe it. It is causally disconnected from you for the rest of time. 94% of the galaxies in the observable universe are already beyond this horizon, already unreachable, already, for all practical purposes, erased from your future. You can still see their light because the photons were emitted when they were closer, but you will never interact with those galaxies again. They are already gone, and it gets worse with time. The expansion is accelerating. The cosmic event horizon is not static. As the universe continues to expand, more and more galaxies will slip beyond it. Within roughly 1 to 2 trillion years, every galaxy outside the local group, the small cluster that includes the Milky Way, Andromeda, and a few dozen smaller galaxies bound together by gravity, will have redshifted beyond the detection threshold. The light from those galaxies will be stretched to wavelengths so long that no instrument could ever detect it. They will not just be unreachable, they will be invisible. But the universe will not merely lose its galaxies to the horizon. It will lose the evidence that those galaxies ever existed. The cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe, the radiation that tells us where we came from and how the cosmos began, that too will be redshifted beyond detection. Within roughly 100 billion years, the CMB will be undetectable by any physically possible instrument. Gone. Not somewhere else. Not hidden. Erased from the observable universe by the expansion of space itself. Think about what this means for a civilization that arises in that future. Astronomers born 2 trillion years from now in a galaxy formed by the merger of the Milky Way and Andromeda, which will collide in roughly 4 to 5 billion years. Those astronomers will look out at the sky and see nothing. One galaxy, their own, surrounded by perfect, featureless blackness. No CMB, no distant galaxies, no evidence of the Big Bang, no evidence of dark energy, no evidence that the universe was ever anything other than a single galaxy in an infinite void. They will have no way to deduce that they live in an expanding universe. They will have no way to discover the cosmological constant. They will have no way to know that the blackness around them is not primordial emptiness, but the result of a process that has been running for trillions of years, pushing everything they might have discovered beyond the reach of light. The universe will have erased its own history, not through destruction, through expansion, through emptiness. This is not science fiction. This is the standard cosmological model played forward in time. Lawrence Krauss and Robert Scherer published the analysis in 2007. The title of their paper was The Return of a Static Universe and the End of Cosmology. Their conclusion was that future cosmologists, no matter how brilliant, no matter how advanced their instruments, would be fundamentally incapable of discovering the true nature of the universe they inhabit. The universe would have hidden itself from them, not through any conspiracy, through physics, through the mathematics of an expanding vacuum that gradually eliminates all evidence of its own expansion. And the emptying does not stop there. The timeline of cosmic death extends far beyond the loss of galaxies and the fading of the CMB. Within roughly 100 trillion years, the last stars will have burned through their fuel. The era of starlight will end. The universe will be populated by stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down, black holes growing slowly by accreting stray matter. But even these remnants are temporary. If protons decay, and several grand unified theories predict they do with lifetimes of roughly 10 to the 34th to 10 to the 40th years, then all ordinary matter will eventually disintegrate. Every atom, every white dwarf, every neutron star converted into leptons and photons and dispersed into the void. The black holes will last longer, but not forever. Hawking radiation, the process that Zeldovich helped inspire during that 1973 meeting in Moscow, ensures that every black hole eventually evaporates. A solar mass black hole would take roughly 10 to the 67th years to evaporate. The supermassive black holes at the centers of galaxies, the ones weighing billions of solar masses, would last roughly 10 to the 100th years. 10 to the 100th. A 1 followed by 100 zeros. A Google. But even that is finite. Even those will end. And when the last supermassive black hole evaporates in a final burst of Hawking radiation, the black hole era ends. What remains is the dark era, a universe containing nothing but photons, neutrinos, electrons, and positrons, all at temperatures asymptotically approaching but never reaching absolute zero, spread across a space so vast that the average distance between any two particles is larger than the current observable universe. Essentially nothing, happening nowhere, forever. In 2020, Matt Kaplan at Illinois State University calculated that there is one last gasp of activity. White dwarfs that have cooled to become black dwarfs, invisible, frozen stellar corpses, could in principle undergo nuclear fusion through quantum tunneling on timescales of 10 to the 1100th years, a number so large it defies comprehension. These hypothetical black dwarf supernovae would be the last events in the universe, the last light. After that, true emptiness, heat death, maximum entropy, the state first conceptualized by Lord Kelvin in 1852, when thermodynamics was young and the universe was thought to be eternal. There is a mathematical description of this endpoint. In 1917, the Dutch astronomer Willem de Sitter, working at Leiden University, published a solution to Einstein's field equations that described a universe with a positive cosmological constant and no matter. De Sitter space, a vacuum solution, a universe that is empty and expanding exponentially, forever. De Sitter was exploring a mathematical possibility. He did not know he was describing the future. Because De Sitter space is where the universe is heading, as matter decays, as black holes evaporate, as everything that is not vacuum energy is converted into radiation and dispersed, the universe approaches De Sitter space asymptotically. Pure emptiness, pure expansion, pure lambda. And here is the part that closes a circle you might not have seen coming. The very early universe, during cosmic inflation, was also approximately De Sitter space. The inflationary epoch was a period of exponential expansion driven by the energy of a scalar field, very similar in structure to a universe dominated by a cosmological constant. The universe began in approximate De Sitter space, and it will end in approximate De Sitter space. It begins and ends with emptiness. Everything in between, every star, every galaxy, every planet, every living thing, every thought you have ever had is a temporary deviation from the vacuum, a fluctuation, a brief local departure from the emptiness that is both the origin and the destination. This is not metaphor. This is the mathematics. And in the middle of all this, between the emptiness that began the universe and the emptiness that will end it, there is a man who deserves far more credit than history has given him for understanding what expansion actually means. Georges Lemaitre was born on July 17th, 1894, in Charleroi, Belgium. He survived the First World War, serving as an artillery officer, and then did something almost nobody else has ever done. He pursued physics and the priesthood simultaneously. He was ordained as a Catholic priest in 1923. That same year, he went to Cambridge to study under Arthur Eddington, then to Harvard to work with Harlow Shapley, then to MIT, where he completed his doctorate. He returned to the Catholic University of Louvain as a professor in 1927. And in that year, 1927, working alone, Lemaitre solved Einstein's field equations for an expanding universe. He derived a relationship between a galaxy's distance and its recession velocity, the relationship that would later be called Hubble's law. He did this 2 years before Edwin Hubble published his observations in 1929. He published in French in an obscure Belgian journal, and almost nobody noticed. Einstein noticed. Lemaitre presented his work to Einstein in person at the 1927 Solvay conference. Einstein's response was devastating. Vos calculs sont corrects, mais votre physique est abominable. Your calculations are correct, but your physics is abominable. Einstein, who had introduced the cosmological constant specifically to prevent the universe from expanding, could not accept that his own equations predicted expansion when lambda was removed. Einstein was wrong. Lemaitre was right, and Einstein eventually admitted it. By 1933, Einstein publicly stated that Lemaitre's understanding of general relativity was among the deepest present. The static universe was dead. Expansion was real. But the story of Lemaitre's credit is itself a kind of erasure. When his 1927 paper was translated into English in 1931, the key paragraph estimating the expansion rate was missing. For decades, historians assumed the translation was deliberately censored, perhaps by Eddington or others who wanted to preserve Hubble's priority. In 2011, Mario Livio found archival evidence showing that Lemaitre himself had removed the paragraph, apparently out of a lack of concern for establishing priority. He erased his own contribution, quietly, without complaint. And here is the irony that connects Lemaitre to this story. Lemaitre's theory of the primeval atom, the idea that the universe began from a single quantum of enormous energy, was mocked by Fred Hoyle, the British astronomer who coined the term Big Bang in 1949 as a joke, a put-down. The name stuck. Lemaitre, a Catholic priest, proposed the theory. Hoyle, an agnostic who preferred a steady-state eternal universe, named it. When Pope Pius XII tried to proclaim the primeval atom as scientific validation of Genesis in 1951, Lemaitre, the priest, talked him out of it. He insisted that his theory remains entirely outside any metaphysical or religious question. The man who discovered the expansion of the universe refused to let it be used as theology, and the man who named the expansion as a joke became friends with the man he mocked. Lemaitre and Hoyle took a driving vacation together through Europe after a Vatican Observatory meeting in 1957. The universe does not care about our categories. Lemaitre predicted the expansion. The expansion is now erasing the universe. The universe expands into de Sitter space, pure vacuum, pure emptiness, the same state it began in. And the man who first understood this process was a priest who erased his own name from the discovery and refused to let anyone, including the Pope, claim to understand what it meant. The emptiness is growing. Every second, more of the universe slips beyond the cosmic event horizon. Every second, the distance between galaxy clusters that are not gravitationally bound increases. Every second, the future gets emptier. And now there is evidence that the force driving this emptiness might itself be changing. In April of 2004, the Dark Energy Spectroscopic Instrument, Decay, released its first-year data. 6 million galaxy redshifts, spanning the range from z equals 0.1 to z equals 4.2. The results showed a preference for a dark energy equation of state that was not constant. Specifically, the data favored a model where the dark energy parameter W was greater than -1 in the recent past and less than -1 in the deeper past, with a time evolution that deviated from a pure cosmological constant at 2.5 to 3.9 sigma significance. In March of 2200, Decay released its second dataset, 14 million redshifts. The precision on baryon acoustic oscillation measurements reached roughly 0.24%. The evidence for evolving dark energy strengthened to 2.8 to 4.2 sigma, depending on which supernova dataset was used in combination. Will Percival, a Decay project spokesperson, said it was looking more and more like they might need to modify the standard model. If this holds, if dark energy is changing over time, then the cosmological constant is not a constant. It is a field, a dynamical entity that can evolve. The data suggests dark energy may have peaked around a redshift of 0.45 and is now weakening. The implications are profound and uncertain. A weakening dark energy could mean the expansion eventually decelerates, or it could mean something worse. In some models, a changing vacuum energy is a sign of instability, a sign that the vacuum is not in its final state, that it is evolving toward what nobody can say. This is not yet confirmed at the 5 sigma discovery threshold. The Decay team is cautious. The supernova systematics are complex, but the trend line is clear, and every new dataset has strengthened it rather than weakened it. Euclid, the European Space Agency Space Telescope, launched in July 2003, is conducting a survey that will ultimately observe over 1.5 billion galaxies. Its first cosmology results are expected in 2206 or 2007. The Vera Rubin Observatory, named after the woman who proved dark matter exists and never received the Nobel for it, will discover roughly 300,000 new supernovae per year when it begins full operations. The data is coming, and it may tell us that the emptiness is not just growing, but changing. But there is one final layer to this story, one final descent, because everything I have told you so far, the vacuum catastrophe, the cosmic voids, the Hubble tension, the accelerating expansion, the timeline of cosmic death, all of it assumes that the vacuum state we currently inhabit is stable, that the emptiness might be wrong, might be inexplicable, might be growing, but at least it is permanent. At least the floor is the floor. The Higgs boson measurement from 2012 says otherwise, and that is where this story ends, or rather, where it opens into something we cannot close. On June 15th, 1980, 2 physicists published a paper in Physical Review D that described the end of the universe. Not the slow heat death, not the gradual fading of stars and evaporation of black holes. Something faster, something total, something you would never see coming. Sidney Coleman was at Harvard. Frank DeLucia was at Stanford and the Institute for Advanced Study. Their paper was called Gravitational Effects on and of Vacuum Decay. It has been cited over 1,300 times. The math is elegant, the conclusions are terrifying, and the abstract betrays nothing of the horror inside. Here is what they showed. In quantum field theory, a vacuum state is a configuration of fields at their lowest energy. Think of it as a ball sitting at the bottom of a valley, stable, settled. But quantum field theory allows for the possibility that the valley you are sitting in is not the deepest valley. There might be another valley, lower than yours, separated by a hill. Your valley is a local minimum. The other valley is the global minimum. You are in a false vacuum. The true vacuum is elsewhere. In classical physics, the ball stays in the local minimum forever. It does not have enough energy to climb over the hill. But in quantum mechanics, there is tunneling. The ball does not climb the hill. It passes through it. Quantum tunneling is not a metaphor. It is a measured, confirmed, routinely exploited phenomenon. It is how nuclear fusion works in the sun, how scanning tunneling microscopes image individual atoms, how alpha decay happens, and Coleman and DeLucia showed that it can happen to the vacuum of the universe. The process is called bubble nucleation. A tiny region of space, through a quantum tunneling event, transitions from the false vacuum to the true vacuum. This region, the bubble, has lower energy than its surroundings. The energy difference drives the bubble wall outward. In the absence of gravity, the wall accelerates to the speed of light. In the presence of gravity, Coleman and DeLucia showed that the dynamics are more complex, but the qualitative result is the same. The bubble expands rapidly, and inside the bubble, the laws of physics are different, not subtly different, fundamentally different. The vacuum state determines the values of physical constants, the masses of particles, the strengths of forces. A different vacuum means different particles, different forces, different chemistry. Inside the bubble, atoms as we know them might not exist. Water might not be possible. Carbon might not be stable. Life in any form we can conceive of would be impossible. The bubble does not destroy the universe in the way you might imagine destruction. It replaces it with something else entirely, something that follows different rules, something we could not predict and would not recognize. And the bubble wall would be invisible. It moves at or very near the speed of light. No signal can outrun it. No warning can precede it. The wall and the light announcing its arrival reach you at the same moment. By the time any instrument could detect the transition, the instrument and the physicist reading it and the planet they are standing on would already be inside the new vacuum, already rewritten. Coleman and DeLucia noted, with a dryness that physicists are famous for, that the gravitational effects generally make vacuum decay less probable. Gravity, in many cases, stabilizes the false vacuum, making the tunneling rate astronomically small. This is reassuring, in the way that being told the gun is not loaded but the safety might be off is reassuring. Now, why does this matter right now? Why is this not just a theoretical curiosity from 1980? Because of a number, 125.25 plus or minus 0.17 giga-electron volts. That is the mass of the Higgs boson, measured at CERN in 2012 by the ATLAS and CMS experiments at the Large Hadron Collider. The announcement was made on July 4, 2012. Peter Higgs, then 83 years old, was in the audience. He wept. The discovery confirmed the last missing piece of the standard model of particle physics and won Higgs and François Englert the Nobel Prize in 2013. But the mass of the Higgs boson is not just a confirmation of the standard model. It is a diagnostic of the vacuum. The stability of the electroweak vacuum depends on two numbers: the mass of the Higgs boson and the mass of the top quark, which is approximately 172.76 giga-electron volts. Together, These two masses determine the shape of the Higgs potential, the energy landscape that the Higgs field sits in. And the shape of that landscape is not reassuring. In 2012, Giuseppe Di Grassi and colleagues calculated that absolute stability of the electroweak vacuum is excluded at 98% confidence for a Higgs mass below 126 GeV. The measured mass is 125.25, below the threshold. In 2013, Dario Buttazzo and colleagues at the CERN Theory Division published a more detailed analysis. Their conclusion was precise and unsettling. The measured values of the Higgs mass and the top quark mass place our universe in the metastable region of the phase diagram. Not stable, not unstable. Metastable, balanced on a ledge. Specifically, they found that the Higgs self-coupling parameter, lambda, turns negative at energies around 10 to the 10th GeV. This means the Higgs potential, the energy curve that determines the vacuum state, develops a second minimum at high field values, a minimum that is lower than the one we currently occupy. A true vacuum, deeper than ours, and our vacuum, the one that makes atoms and chemistry and biology and consciousness possible, is perched on a local minimum above it. Buttazzo and colleagues used a particular word to describe our position on the phase diagram: near criticality. We are not deep in the metastable region. We are not comfortably far from the stability boundary. We are right at the edge, almost exactly on the line between stability and metastability. This near criticality is itself a mystery. Why should the measured values of the Higgs and top quark masses place us so precisely on the boundary? Is it a coincidence? A selection effect? A sign of unknown physics? Nobody knows. The calculated lifetime of the electroweak vacuum in its current state is enormously long, far longer than the age of the universe. The probability of a tunneling event occurring anywhere in the observable universe within the next 14 billion years is vanishingly small. You are safe, probably, for all practical purposes. But for all practical purposes is carrying more weight in that sentence than you might want it to. The lifetime calculation assumes a vacuum at zero temperature, unperturbed by any external influence. High-energy particle collisions, conditions near black holes, or unknown physics at energy scales we have not probed could in principle seed a tunneling event. The LHC was briefly the subject of public concern on this point, and the physics community correctly pointed out that cosmic rays produce far higher energy collisions than the LHC every day, and the universe is still here. That argument is sound, but it is an argument from observation, not from theory. The theory says the vacuum is metastable. The observation says it has not decayed yet. Those are not the same statement. And then there is the connection to the vacuum catastrophe. Think about this. The vacuum energy is 120 orders of magnitude lower than quantum field theory predicts. Nobody knows why. The Higgs potential shows that our vacuum is not the true ground state. It is a local minimum. Somewhere in the energy landscape, there is a deeper minimum with different physics, and the string theory landscape contains 10 to the 500th power possible vacuum states, most of them with different cosmological constants, most of them with values that would not allow structure to form. Put these facts together, and the picture that emerges is not comforting. The emptiness that makes your existence possible is balanced on a ledge. Below you, somewhere in the vast landscape of possible vacuum states, there is a true minimum that you cannot see, cannot predict, and cannot prevent yourself from falling into. The vacuum energy is too small by a factor that no theory can explain, and the potential curve of the Higgs field drops exactly where the models say it drops. And the position of our vacuum on the phase diagram is right at the boundary between lasting forever and not lasting forever. The emptiness is not a settled question. It is an open wound in physics. The voids are too large. The vacuum energy is too small. The expansion is too fast and possibly changing. The Hubble constant disagrees with itself. The Higgs potential drops into a deeper minimum that nobody asked for and nobody can explain. And the universe, the whole thing, from the quantum fluctuations in your desk to the cosmic event horizon 16 billion light-years away, is sitting on a vacuum state that mathematical physics classifies as metastable, not unstable, not doomed, metastable. A word that means stable for now. Earlier I told you about the cosmic event horizon, how 94% of the observable universe is already beyond it, how the universe is erasing itself through expansion, how future civilizations will never know what we know. That process, the slow erasure, the march toward the sitter space, is the optimistic scenario. It assumes the vacuum holds. It assumes the metastable ledge does not give way. It assumes the emptiness continues to be the kind of emptiness that permits atoms and stars and minds. If the vacuum decays, the erasure is not slow, it is instant. A bubble nucleates somewhere. Could be here, could be 10 billion light-years away. It does not matter. The wall moves at the speed of light. There is no observation that precedes its arrival. There is no warning sign. There is no intervention possible. The physics inside the bubble does not include the physics that makes you. It does not include chemistry. It does not include thought. It does not include memory. It does not destroy you the way a bomb destroys you, leaving wreckage and evidence. It replaces you. It replaces the space you occupied with a space that has different rules. Rules that do not include anything you would recognize as existing. And here is the final connection. The vacuum energy problem, the 120 orders of magnitude discrepancy, might not be a bug. It might be a feature. The emptiness might be the signature of a vacuum that has not yet found its ground state. The reason the energy is so much lower than predicted might be that our vacuum is a transitional state, an intermediate stop between the violent quantum vacuum that the equations predict and the true vacuum that lies beneath. The emptiness is not the answer. It is the question the universe has not yet finished asking. The cosmological constant problem, the cosmic voids, the Hubble tension, the accelerating expansion, the metastable Higgs potential. These are not 5 separate problems. They are 5 symptoms of the same underlying condition. Something is wrong with empty space. Something fundamental. Something that the entire apparatus of modern theoretical physics, with all its beauty and all its precision, cannot explain. You are made of atoms that are almost entirely void. You are orbiting a star that is separated from its nearest neighbor by a chasm so vast that the fastest object humanity has ever launched will need 40,000 years to cross it. You are sitting inside a void 2 billion light-years across that the standard model of cosmology says should not exist. You are living in a universe where the vacuum energy is 120 orders of magnitude too small for reasons nobody can identify. The universe is expanding. The expansion is accelerating. The acceleration is erasing the evidence of its own history. And the vacuum state that makes all of this possible, the emptiness that you take for granted as the background of reality, is balanced on a ledge in the Higgs potential that the mathematics classifies as temporary. The calculations have been checked. The Higgs mass is what it is. The vacuum energy is what it is. The voids are where they are. And somewhere in the energy landscape beneath your feet, beneath the atoms, beneath the quantum fields, beneath the emptiness itself, there is a deeper minimum, a true vacuum, a floor beneath the floor. If the universe ever finds it, the transition will begin as a point, a single point in space where the quantum fields tunnel through the barrier. The bubble of true vacuum will expand outward at the speed of light. It will carry with it a new set of physical laws, new constants, new particles, new forces, a new definition of empty. Inside the bubble, nothing that exists in our vacuum will persist. Not atoms, not light, not the geometry of space itself, just a different kind of emptiness, one that was always there underneath, waiting. You will not see it. You will not hear it. You will not feel it. By the time the light from the bubble wall reaches your eyes will no longer exist, not because they were destroyed, because they were replaced by something that does not need eyes, that does not need light, that does not need you. And the emptiness, at last, will be complete.